Hello everyone. Today we are going to study about the D and F block elements theory part 7. So let's begin our today's topic NCERT chapter 4 D and F block elements theory part 7, and today we are going to cover the NCERT section 4.6 to 4.6.4. This is disclaimer. The objective of today's lecture, so after attending this lecture you will be able to understand the general characteristics of F block elements and the general horizontal and the group trends in them. You will be able to describe the properties of F block elements and give a comparative account of actinoids with respect to their electronic configurations, oxidation states, and chemical behavior. The topics that we are going to cover according to the NCERT, the first section 4.6, that is the actinoids. The section 4.6.1 electronic configurations, section 4.6.2 ionic sizes, section 4.6.3 oxidation states, section 4.6.4 general characteristics and comparison with lanthanoids, and lastly we will solve an example 4.10 and conclude with the summary. So let's begin with our first topic, that is 4.6, the actinoids. Actinoids include the 14 elements from thorium to lawrencium. Okay, previously we have covered in the F block elements about the lanthanoids. There also we have talked about the 14 elements after lanthanum which covered under the lanthanoid series. Here in the actinoid we include it includes 14 elements from thorium to lawrencium. The names, symbol, and some properties of these elements are given in the table 4.10. So according to this table, we have given actinoids, where actinoids are present from thorium to lawrencium. So thorium, protactinium, uranium, neptunium, plutonium, americium, curium, berkelium, californium, einsteinium, fermium, mendelevium, nobelium, and lawrencium from atomic number 90 to 103. So these are the 14 elements from thorium to lawrencium coming under the actinoid series. We will see, we have seen the names and the like the symbols and the atomic numbers. The property we will see. So the actinoids are radioactive elements, that means they decay with the time, and the earlier members in the actinoid series have relatively long half-lives, and the later ones have half-lives values ranging from a day to 3 minutes for lawrencium. Okay, so lawrencium, whose atomic number is 103, having only 3 minutes of half-life. Okay, in the earlier members of this series like thorium and protactinium, they are relatively have longer half-lives than the later elements in the series. The later members could be prepared only in the nanogram quantity because they are very radioactive element. They decay like very fast. That's why they have very lesser half-life, and due to which they could be prepared only in the nanogram quantities. Nanogram means 10 to the power minus 9. Actinoid series elements and its mnemonic. So let's see actinoid series elements and their mnemonic. So एक था पागल उल्लू नेपाली उसके पुराने आम कम बिके उसने कॉफी ऐसी फरमाई मैडम नूडल लाई. Okay, so you can see this in this table where there is given element symbol, their element name, their mnemonic word in the Hindi and in the English separately. Okay, so tha is for th, that is thorium. Pagal is for Pa, that is protactinium. Ullu is for U, that is uranium. Nepali uske neptunium Np. Purane Pu, plutonium, Am, americium, cum, Cm, for curium, Bk उसने, Bk for berkelium, coffee, Cf for californium, Ac, einsteinium for Es, fermi, Fm for fermium, madam, Md for mendelevium, noodle, No for nobelium, and Li, Lr for lawrencium. Okay, so this is how, using the mnemonic words, you can remember the series of the actinoids or the elements, that which element is coming after which one. So let's talk about the electronic configurations of actinoids, covering the NCERT section 4.6.1. So let's see first of all the general atomic configurations. General formula for electronic configuration of actinoids is 5Fn 6D022 7s2. So in each element of the actinoid, 7s2 is going to be present there, but the electrons is going to be filled in the 6d orbital from 0 to 2 and 5Fn. Okay, F orbital is like from the fifth shell. All the actinoids are generally believed to have a 7s2 electronic configuration for their outermost shell. So every every element in the actinoid series are going to have 7s2 electronic configuration in their outermost orbital. The primary variation lies in the variable occupancy of 5f and 6d subshells. Okay, so the primary variation in the electronic configurations lies in variable occupancy of 5f and the 6d subshells in the elements. You can see this table where the property in this column is given, like electronic configuration in the M3 positive state, electronic configuration in the M4 positive state, and these are the elements coming in the actinoids series. Okay, so actinoid, thorium, protactinium, uranium, neptunium, and up to lawrencium, they are there. Okay, so if you observe, the 7s2 is going to be present in all the elements configuration in this series, right? And the 5f and the 6d subshells are going to be filled, like if you observe here in the protactinium, we have 5f2 and 61. Similarly, 5f3, 61, 5f4, 61, right? Again, here at the curium, we have 5f7, 61, and then at lawrencium 5f14, 61. Okay, so this is a variation between the variable occupancy of 5f and 60 subshells in different elements. Let's see the irregularities and stability. So similar to the lanthanoids, there are irregularities in the electronic configurations of actinoids. These irregularities are directly related to extra stability associated with empty, that is F0, half filled, that is F7, and completely filled, that is F14 occupancies of the 5f orbitals. Okay, so why the irregularities has been observed in the actinoids? These irregularities are related to the extra stability gained by the elements in the actinoid series, which associated with their empty, either they have empty F0 orbital due to which they are going to attain a noble configuration, or either they are having half filled configuration F7 and completely filled F14 configuration, which is a stable one, of 5f orbitals. Okay, so 5f, okay, f is a orbital that can contain maximum of 40 number of electrons. That means half filled will be 7, right? So f7 and f14 both are more stable, half filled and completely filled. And empty filled f0, that means the element is going to attain the noble gas configuration, due to which it is going to gain extra stability. Okay, and due to which there are having some irregularities in the electronic configurations of actinoids. So let's see the examples. So configuration of americium. So if you see Am, okay, the configuration of for this element is Rn radon 5F7 7s2. Okay, now this shows a stable half-filled F7 configuration. You can see we have 5F7. F7 means that uh, half of this f orbital has been filled with the electrons. Okay, that means 7 paired electron is present in it. That means this is half filled stable configuration, okay, which is present in the americium, that is Am, radon 5F7 7s2. Configuration of curium is Rn 5F7 61 7s2, right? This also features a stable half filled, that is F7 configuration, with an additional electron in the 60. Other than the 7s2, which is going to be present in every element, there is 61 electron, and the 5F7 half filled stable configuration present for the configuration for curium. Participation of 5F electrons in the bonding. So let's talk about on this topic, that how the 5F electrons, the electrons which are occupying in the 5F orbital, is going to be participate in the bonding. While the 5F orbitals structurally resemble the 4F orbitals in terms of their angular part of the wave function, so basically we are saying that 5F and the 4F orbital are similar, are having similar angular shapes. Okay, so they resemble from each other. So there's a crucial difference. First, 5F orbitals are not as buried or deeply shielded as the 4F orbital. If you compare between the structure, okay, like the presence or at the position of the electrons which are filled in the 4F and the 5F orbital inside an atom, so 5F orbitals are not as buried or deeply shielded as the 4F orbitals, right? 5F electron are less deeply embedded within the atom's electron cloud, right? And consequently, the 5F electron can participate in the bonding to a far greater extent than 4F electron due to this reason, right? So inner electron shield outer electron from nucleus positive charge. So 4F orbitals are more shielded by inner electrons. So they are less likely to participate in the bonding compared to the 5F electron, and that's why it will cause greater accessibility of 5F electron for the bonding. So 5F electron can participate in bonding at a far greater extent than the 4F electrons. Now let's move to our next section, 4.6.2, that is ionic sizes. So let's first of all observe a general trend in the actinoid contraction. So a gradual decrease in the size of atoms, or M3 positive tripositive ions, is observed across the actinoid series. As similarly, like in the lanthanoid series, we have seen the gradual decrease in the tripositive ion sizes, right? Here also we have observed a gradual decrease in size of atoms or tripositive ions. And this phenomena of gradual decrease is referred to as actinoid contraction here in the case of actinoid series. If you see this table where the atomic number is given from 89, 90, 91 to 103, and the name of the element associated with these atomic numbers, like for 89 we have actinium, for 90 we have thorium, for 102 we have nobelium, and for 103 we have lawrencium, right? Similarly, their symbols are given. For 89, for actinium, symbol is AC. Similarly, for 103 atomic number, element name is lawrencium, and the symbol is LR. Similarly, the radii is given in the picometers for tripositive ions and the M4 positive ions. Okay, so some of the radii are given for some elements. You can observe this table. The contraction from one element to the next in the actinoid series is greater than in the lanthanoid series. Okay, now if you see, it is decreasing from 111 to 103, then 101, then 100, then 99, 99, 99, 99. It is decreasing, right? Similarly, here also the radii is decreasing. So this contraction from one element to the next in actinoid series is greater than in lanthanoid series. If you compare here, the contraction is happening in the actinoid series with a greater extent than in the lanthanoid series. This more significant contraction is a direct result of even poorer shielding provided by the 5f electrons compared to the 4f electrons. So why there is this significant contraction in the sizes? It is a result or direct result of poorer shielding provided by the 5f electrons if you compare with the 4f electrons present in the lanthanoid series. Now let's talk about our next section, that is 4.6.3, oxidation states. So let's see the oxidation states of actinoids. Actinoids exhibit a diverse range of oxidation states, which is a key characteristics differentiating them from lanthanoids. Okay, so if you compare with the lanthanoids, actinoids having various or diverse range of oxidation state they show, which is a key characteristic used to differentiate between the lanthanoids and the actinoids. Okay, because lanthanoids haven't this property of showing diverse range of oxidation state. Greater range of oxidation states. So actinoids show a greater variety of oxidation states if you compare to lanthanoids. Okay, so comparatively from the lanthanoids, actinoids show variety of oxidation states. This wide range of oxidation state is partly attributed to the fact that the 5f, 60 and 7s energy levels are of comparable energies, allowing more electrons to participate in the bonding. Okay, so this 5f, 60 and 7, okay, so how can you get the energy of these? By using the n plus l rule, right? So let's suppose if you want to calculate for these three, first for 5f, the n is 5 and the l will be, for f, l will be 3, right? So 5 plus 3 is 8. Now if you calculate for 6d, it will be 6 plus 2, right? So 6 plus 2 is again 8. Here 7s is going to be 7 because for s, the L value will be 0, right? So the lowest value of the energy is for this 7s. Then comes the 5f and then comes the 60. Because lower, if you have the same energy value, then you take or you consider the lower n value orbital. So it will be 5f. So 7s, 5f, 60. Yes, 7 is having 7 energy and 5 and 60 having 8 energy. So they are of comparable energies. These three orbitals or these three energy levels are of comparable energies, which allowing them for more electrons to participate in the bonding. Okay, and that's the reason that why this wider range of or variety of oxidation state is shown by the actinoids. Common and highest oxidation state. So we have also seen in the lanthanoids that the common oxidation state was +3, right? Here, let's see what is the common and the highest oxidation state shown by the actinoids. So the +3 oxidation state is generally shown by all the actinoids. You can see in this table from actinoid, thorium, plutonium, uranium to lawrencium, protactinium, okay, protactinium, uranium, and neptunium to lawrencium. These are given the oxidation state shown by the each element. So actinium, actinoid show +3 oxidation state, thorium show +4, and protactinium show +3, +4, and +5. Uranium show +3, +4, +5, +6, and neptunium show +3, +4, +5, +6, +7. Similarly, plutonium show +3, +4, +5, +6, +7, and americium show +3, +4, +5, +6, and this curium show +3 and +4, and berkelium show +3, +4, californium show +3, and after that every element show +3 oxidation state, right? So the +3 oxidation state is the one that is generally shown by all the actinoids present in the series. Elements in the first half of the series frequently exhibit higher oxidation state, right? In the first half of series, if you observe, uh, elements are going to show the oxidation state in a frequent higher manner, like +3, then increase to +4, then increase to +5. The oxidation state, highest oxidation state shown by an element. So +3, +4, +5, +6, +7. So they are frequently increasing. The maximum oxidation state increases from +4 in the thorium, that is this, +5 in the protactinium. Okay, protactinium has +5 maximum oxidation state. +6 in the uranium. Uranium has +6 oxidation state maximum. In the neptunium, that is Np, +7 is the maximum oxidation state. Np, that is neptunium, show the highest +7 oxidation state, right? And after neptunium, maximum oxidation state is decreasing in the succeeding elements. Okay, so after this neptunium, with each element, succeeding element, the oxidation state is decreasing. For example, plutonium is having +7. It is showing +7 oxidation state, but after it, the americium comes, which show only +6, and then curium, which only go up to +4. So the oxidation state is decreasing after the neptunium in the succeeding elements. Okay, from +7 to +5, +6, +4, and +3. Similarities with the lanthanoids. Now we observe the similarities of actinoids with the lanthanoids. So similarity, actinoids resemble lanthanoids in having more compounds in the +3 state than in the +4 state. Okay, this is common in the actinoid and lanthanoid, that actinoids also is having more number of compounds in the +3 oxidation state than in the +4 or any other oxidation state, right? Because if you observe, every element in the actinoid series is going to have +3 oxidation state. Same was observed in the lanthanoids. The key behavior is that both +3 and +4 actinoid ions tend to hydrolyze. That means they are going to react with water, which are present in both +3 and +4 oxidation state. Actinoid oxidation states vary widely, so their chemistry depends on the factors beyond just oxidation state. Okay, so actinoid oxidation states vary widely. That means they show a variety of oxidation states, right? So their chemistry also depend on the factors which are beyond just oxidation state. So let's see our next section, that is 4.6.4, general characteristics and comparison with the lanthanoids. So let's see the general characteristics of actinoids. First, physical appearance and structure. So actinoid metals are all silvery in the appearance. They display varied structures, and due to the irregular metallic radii, which are significantly larger than those of lanthanides. Okay, so why they display varied structure? Due to the irregularity in their metallic radii, which are significantly larger than those of lanthanoids. That means the irregular metallic radii which you have seen in the lanthanoids, here in the actinoid it is larger. The reactivity, if you talk about the reactivity of actinoids are highly reactive metals. That means especially when in a finely divided state. Actinoids are highly reactive metal. They react very like much, and they are highly reactive, especially when they are in finally divided state. Okay, reaction with the water. So they show reaction with water. Boiling water reacts with them, with actinoids, to produce a mixture of oxide and hydride. So when actinoids are going to react with the boiling water, they are going to produce a mixture of oxides formed by the water and the hydride, okay, formed by the reaction between actinoids and water. Now reaction with nonmetals. When it happens, the actinoid and the nonmetal reaction, they combine, with most known metals at the moderate temperature. So at moderate temperature, the actinoids and the non-metals are combined. Reactions with acids and bases. What happens when actinoids react with acids and base? So hydrochloric acid attack all the actinoid metals, HCl. Okay, hydrochloric acid can attack all the actinoid metals. Most are only slightly affected by nitric acid because of the formation of protective oxide layers on their surface. And most of the actinoids are slightly affected, a very little affected by nitric acid. Why? Because when they react with nitric acid, the formation of a layer, which is a protective oxide layers, form on the surface of the metal. And alkalis, group 1 elements, have no action on the actinoid metal. So alkalis means base. So base have no action on actinoid metal. When you react actinoids with the bases, they give no reaction. Hydrochloric acid attack. Hydrochloric acid reacts with actinoid metals, right? Nitric acid, in which nitric acid cannot that much affect the actinoids because of the formation of protective oxide layer. And alkalis base have no reaction on the actinoid metals. So this we have talked about the physical property and the chemical properties or the reactivity of actinoids. Now let's talk about the magnetic properties. So the magnetic properties of actinoids are more complex than those of lanthanoids. If you compare with the lanthanoids, here in the case of actinoids, they are having more complex magnetic properties. While there is a rough parallel in how the magnetic susceptibility varies with the number of unpaired 5f electrons compared to 4f electrons in the lanthanoids, and the lanthanoids generally have higher magnetic susceptibility values. Okay, magnetic susceptibility is basically how much a material becomes magnetized in an applied magnetic field. That is what is telling about telling magnetic susceptibility. Okay, so there is a rough parallel in how this vary with the number of unpaired electron present in 5f electrons. If you compare the unpaired electron present in the 4f electron in lanthanoids, and if you compare the lanthanoids, generally have higher magnetic susceptibility, that means higher magnetized value than present in the actinoids. Let's talk about the ionization enthalpies. So it's evident that ionization enthalpy of early actinoids are lower than those of early lanthanoids. Okay, so if you remember from the lanthanoids, the early member or you can say the first ionization enthalpy shown by the lanthanoids was 600 kilojoule per mole. And here we are saying that it is evident that ionization enthalpies of early actinoids are comparatively lower than those of early lanthanoids, though exact values are not accurately known. What is the reason behind this lower ionization enthalpy value? So when 5f orbitals begin to be occupied, they penetrate less into the inner core of the electrons, right? So when the orbital of 5f is going to be occupied by the electrons, they are lessly embedded within the atom's electron cloud in the inner core of the uh, electrons, right? And consequently, 5f electrons are more effectively shielded from the nuclear charge than the 4f electrons in the corresponding lanthanoids. In the lanthanoids, if we have talked about the 4f shielding, the poor shielding shown by the 4f orbital. Here, the 5f electrons are more effectively shielded from the nuclear charge. That means they can easily participate in the bonding to form the bond with various elements. They are shielded with the nuclear charge from the nuclear charge. Okay. Then the 4f electrons in the corresponding lanthanoids. And because of the outer electrons less firmly held, that means 5f electrons are because less firmly held, they are more available for bonding in the actinoids. and this explains their greater reactivity and wider range of oxidation states they show. Okay, and due to which, like this reason of availability of IFF electrons, because it is more effectively shielded from the nuclear charge. This reason is uh, self-explanatory for the greater reactivity shown by the actinoids and the wider range of oxidation state they show. Let's compare with the lanthanoids. So delayed similarities. So behavior similar to that of lanthanoid is not evident until the second half of the actinoid series. Okay, similar to that of the lanthanoid series, the behavior is not evident until second half of actinoid series. The second half, the after the one which was showing +7 oxidation state. Remember? So in the early actinoids, despite this, even the early actinoid resemble lanthanoids in showing close similarities among themselves and a gradual variation in the properties that do not involve a change in oxidation state. So in the early actinoids, you have observed that they resemble with the lanthanoids in showing close similarities among themselves. Okay, because they show very close similarities among themselves and a gradual variation in the property that do not involve a change in oxidation state. And in the properties, they show gradual variation, they show differences that is not going to be involved the change in the oxidation state property. So we are talking about early actinoids. Now, extended effects of contraction. Lanthanoid and actinoid contractions both have extended effect of sizes, both have extended effects on sizes and consequently the properties of elements succeeding them in their respective periods. Okay, so both the contraction of lanthanoid and the lanthanoid in the case of lanthanoid series, actinoid contraction in the case of actinoid series, they have their effects on size and consequently the properties of the elements present in both the series succeeding them in their respective periods. The lanthanoid contraction is currently considered more important primarily because the chemistry of elements succeeding the actinoids is much less known at present, because as I said that they are very later actinoids are found in nanogram quantity, they are very radioactive, their half-lives are very low, right? So lengthen and contraction is currently more important because the chemistry of elements which is succeeding the actinoids, and that means which are coming in the actinoid series, is much less known at present or after the actinoid series. The elements chemistry is lesser known today. Okay, let's solve an example 4.10 covering the NCERT section 4.5. The example include that name a member of lanthanoid series which is well known to exhibit +4 oxidation state. So you have to tell a member of lanthanoid series which is well known to exhibit the +4 oxidation state. So you have given some time. Try to remember the table we have seen in the lanthanoid series or the examples we have discussed about the lanthanoid series element which show +4 stable oxidation state. And then we will see the answer. Okay, let's see. So for this example, we have seen cerium that is going to display a +4 oxidation state, as a result having more stable configuration, electronic configuration, that is 4f0 in the form of Ce4+. Okay, because when cerium going to lose its 4 electrons from 2 from 6s2, 1 from 5d1 and 1 from 4f1, it is going to attain a noble gas configuration of xenon, which is a stable configuration. Okay, so cerium displays a stable uh, +4 oxidation state, which is a member of lanthanoid series. So correct answer for this example is cerium. Okay, so let's see the summary. So today we have covered the NCERT section 4.6 to 4.6.4. First of all, we have talked about the actinoids. It comprises 14 elements from thorium to lawrencium. We have seen that the actinoid are radioactive elements. We have talked about their half-lives and said that earlier members in the actinoid series have relatively longer half-lives than the later members. Later members have shorter half-lives, from a day to 3 minutes for lawrencium, whose atomic number is 103. The later members can only be prepared in the nanogram quantities. Then we have seen about the actinoid electronic configuration. So 7s2 outer shell outer shell configuration, which is going to be present in all the elements of actinoid series, and variable 5f and the 60 occupancy will be there in some of the elements. 5f filling starts from protactinium, that is Pa, and not from the thorium. If you observe the electronic configuration, the 5f orbital is going to start fill from the element protactinium. The irregularities in the electronic configuration has been observed due to the F0, F7 half-filled configuration stability and F14 full-filled stability. 5f electrons participate more in the bonding than the 4f electrons, leading to a complex chemistry. Okay. Then we have talked about the actinoid contraction. Gradual decrease in atomic or M or positive ion size across the series, similar to the lanthanoids, and we call it as actinoid contraction. Greater contraction than lanthanoids here is present in actinoid due to the poorer shielding by the 5f electrons compared to the 4f, which is present in the lanthanoids. Then we have talked about the oxidation states. There is diverse oxidation states shown by them. So greater range than lanthanoids of oxidation state is shown by actinoids due to the comparable energies of the 5f, 60 and 7s orbital, which is present in the outermost orbital configuration of the actinoid series. The common and the highest states. So the +3 oxidation state is the common for all the elements in the actinoid series. The maximum oxidation state is increasing to +7, shown in the neptunium in the first half of the series, and after neptunium there is a decrease in the oxidation state in the succeeding elements in the actinoid series. The similarities and differences we have seen. So the similar to lanthanoid property, that the more compounds in +3 oxidation state is formed in actinoids than in the +4 oxidation state, similar to the lanthanoids. Both the +3 and the +4 ions hydrolyze, that means they react with water. The complexity, so uneven distribution of oxidation states among the elements of actinoid series makes a sole review based on them unsatisfactory. And then we have talked about the general characteristics of actinoids, like physical characteristic, that they are silvery, they have variable structures due to the greater metallic radii irregularity present in them. Then the reactivity they have shown, so they are highly reactive. The actinoids are highly reactive. They react with water or non-metals. They are also attacked by hydrochloric acid, and they are passivated by nitric acid, because nitric acid, in the case of nitric acid, they form a protective oxide layer over the surface, and there is no alkali reaction observed with the actinoids. Magnetism, so more complex than lanthanoids and generally have lower susceptibility. In the magnetic property, they, due to the magnetism shown by the actinoids, they are more complex than the lanthanoids, and they have generally lower susceptibility. That means lower tendency or lower tendency to make the material magnetized in an applied magnetic field. Then ionization enthalpy, so they show lower ionization enthalpy due to the less shielded 5f electrons, which aiding into their bonding or reactivity. The comparison, so if you compare between actinoids and lanthanoids, so lanthanoid-like behavior appears in the later half of the actinoids, and both the contractions affect subsequent elements like lanthanoid and the actinoid contraction. Both contraction affect subsequent elements, but lanthanoid contraction is currently more significant, more important due to the better understood chemistry of the lanthanoids than comparatively from the actinoids, because actinoids are radioactive. They like uh, occur in a very lower value or in a nanogram quantity, and also their half-lives are also very less. Okay, thank you so much. That's all for today's chemistry session. Thank you.